Greetings, this is Derek Ong, and I've been asked to do the series on PLS for quite some time right now, so I guess it's time for me to give this video a go. So before we begin on the hands-on approach on SmartPLS, I think it would be best if we do a little bit of theory just to explain to you where SmartPLS is compared to other forms of structural equation modeling. Right. As you know, that PLS is what we call the second generation uh, techniques, as you can see here. Now, if you have not watched my first video or first series of videos on SPSS, I suggest that you look through those videos first before coming into this section of the videos. Reason is because you need to understand a little bit about the evolution of data analysis from multiple linear regression before coming to smart PLS. So this is what we call the second generation techniques. So where does smart structure equation modeling come from? Structure equation modeling, as mentioned by Wikipedia, is actually a technique for testing and estimating causal relations using a combination of statistical data and quantitative causal assumptions. So structure equation modeling has its many roots from path analysis, CFA, EFA, multiple linear regression, factor analysis, and of course, right from the very bottom, bivariate correlation. It is also mentioned by one of my gurus or scholars that structure equation modeling is also known as the mother of all statistical modeling. So factor analysis, path analysis, and regression all represent a special case of SEM. So what is SEM? SEM is basically a method that connects multi-item scales into constructs and defines relationship between these constructs. Now this is especially important if you are doing what we call social sciences, because if you notice that a lot of the variables in social sciences are what we call as latent variables. And latent variables are variables that are not easily defined. Now, I'm going to just mention a little bit about latent variables in the outputs. So you notice that this is what we call the measurable items. These are multi-item constructs, and these are what we call the latent construct. So it breaks down into two measurements. One is the measurement model, which uses factor analysis to understand how items measure a particular construct, which is this one. And then when you have many of these latent variables, it just does the structural model, which is the regression equivalent to understand how these constructs relate to each other. Now, structural equation modeling handles very complex relationships between these latent constructs and is able to handle multiple dependent constructs within a single model. This is one of the good things about structural equation modeling, because it can handle multiple dependent constructs, which is an advantage over linear regression, because usually linear regression only handles one dependent construct. However, there are two schools of SEM. One is what we call the covariance-based SEM, and the other one, which we are concentrating on in this series of videos, is the partial least squares SEM. Very quickly, the covariance-based SEM's objective is to reproduce a theoretical covariance matrix without focusing too much on the explained variances. Usually, people who use covariance-based SEM use AMOS as their software. And those people who use the partial least squares SEM or PLS, their objective is to maximize the explained variances on the endogenous latent variables or constructs. And of course, people who usually do this use SmartPLS, and a little bit more detail in the slides coming. As you can see, the two branches or the two schools of structure equation modeling, the and the software that people use, especially when they want to use covariance-based SEM, Lisrael, M+, and AMOS are the more famous ones. And in PLS, PLS Graph, SmartPLS, and Excel Stat is the more famous one. Of course, this series of videos will be looking at SmartPLS. So a little bit more on CBSEM. CBSEM focuses on the goodness of fit, maximization of the difference between observed covariances matrix and the estimated covariance matrix. Usually what people do is that if you notice those people who use um, CBSEM will be more concerned about the chi-square. Yeah, so the chi-square is basically the differences between observed and unobserved variances. And when we look at chi-square for CBSEM, it is always better to have the lower chi-square to ensure that you make sure that the data fits with your model. Yeah, it is good if you're going to be testing and confirm where prior theory is strong. So if you have a strong theory already, then it is always most appropriate for you to use CBSEM. Now, of course, CBSEM assumes quite a lot of things of the classical linear regression model assumptions, which is normality of data, homoscedasticity, which is the constant variance of the errors, and of course, large sample sizes are needed. That is why some people prefer not to use CBSEM, but it all depends on what you want to use. And only reliable and valid variances are useful for testing causal relationships. So in CBSEM, people always tweak their model to ensure that all the causal relationships are valid by looking at the valid variances. And a full information approach is used, means that small changes in the model specification can result in substantial changes in the model fit. So if you want to read a little bit more about these, please also take note that some of my slides have certain references at the bottom that you can look at. So you can pause this video and then just take a look at those references. So an example of how AMOS looks like for the technology acceptance model is one of the examples I'm using here. As you notice that these are your latent constructs, yeah, and each of these are your measurement items. And you also notice that in each of these, the error variances has to be modeled. Yeah, I'm sure you can see that. But in SmartPLS, you can explicitly recognize the measurement models, which means you don't really have to, what's that word, model the measurement errors, whereas in AMOS you need to. And if you're using SmartPLS, it is great if you're using theory development and prediction, or develop a theory and test how this theory is for confirmation, as mentioned by Chin. One of the good things is that it doesn't have to assume normality of data. You can use fewer indicator variables, like 1 or 2 per construct. Sometimes even 1 per construct can be used, which talks about single item measurements. And models can include a larger number of indicator variables, because CBSEM can be difficult if you have more than 50 plus items. Also, one of the advantages that PLS has is that it can model formative constructs. Now, what this formative construct is, I will have another preceding video that explains about the difference between formative and reflective. So please watch for that one. It assumes that all measure variances, including the error, is useful for explanation and prediction of causal relationships. So with the same tab model, this is how it is modeled in PLS. So you notice that these are your constructs, your latent constructs. These are your measurement items. And you notice that there are no error variances model because they are explicitly modeled within it. So where does that leave us? Covariance-based SEM, you use it if you are doing theory testing, strong theory, or PLS modeling if you're going to develop a theory and use that theory to predict, yeah, which is the bulk of the video. And you can use neural networks if you are just fully basing it on machine learning prediction. So I'm going to leave this first video with this slide just to explain to you the differences between PLS and CBSEM. So you can pause this video and look at the various differences. Yeah. So please watch my other videos to continue your learning on SMARTPLS. Thank you.